Hi everyone, this is Nick Banks recording another video for you. You might remember me from the lecture last month about Gaussian integers and the division algorithm for Gaussian integers. That video was actually recorded in the winter 2021 term for a different version of the course, a different offering of the course, but this video is now being recorded specifically for your section, so for the fall 2021 number theory course. And as you can see, the title is Geometry of Pythagorean Triples. So in your previous lecture, Tomasz showed you how to derive a formula for all Pythagorean triples. We'll review what that is in a sec. This video will be about deriving the same formulas, but with pretty much a totally different method, and it'll lead to some interesting discussion about something called algebraic geometry. So let's review all Pythagorean triples. So Pythagorean triples are integers a, b, c with a squared plus b squared equals c squared. You can think of them as, and this is kind of where the name comes from, you can think of them as integers that could be the side lengths of a right triangle. So, and you can refine what a, b, and c are if you want this to be a primitive Pythagorean triple, but it doesn't really matter for this method if they're primitive or not. But all Pythagorean triples are of the form. You derive this set of formulas for a, b, and c. You get a is m squared minus n squared, b is 2mn, and c is m squared plus n squared. For m and n any integers. Again, you can refine what you want from m and n if you want it to be a primitive triple, but it's not too important for us. So any m and n that you choose, it's clear that this gives you a Pythagorean triple. You just check the identity, a squared plus b squared equals c squared. But the hard part of that lecture is showing that any a, b, and c satisfying a squared plus b squared equals c squared can be written in this form for some m and n. And so these are sometimes called Euclid's formulas. Actually, usually it's just called Euclid's formula singular. I don't know why the lack of the plural, but whatever. And so the proof that you saw was elementary in the sense that it doesn't use any deep facts outside of number theory. You can just do it with basic algebra and the elementary number theory you've learned so far. But the way that I'm going to derive the formula, so yes, that is the goal of the video, is to derive those same formulas. We're going to derive Euclid's formula again. But we're going to do it with pretty much a totally different method, and it's using a field called algebraic geometry. It's going to lead into a broader discussion about that. So how do we start? Well, this starts with an observation that Tomasz mentioned in his lecture. We rewrite that equation, the sort of defining equation of a Pythagorean triple, as a over c quantity squared plus b over c quantity squared equals 1. We just divide every term by c squared, and we get this expression. So, in other words, if a, b, and c are a Pythagorean triple, then the tuple, the pair of points a over c comma b over c, is a point. In fact, it's even more important than that. It's a rational point. By that I mean that both entries of that pair are rational numbers because a, b, and c are real integers. So that point is a rational point on the unit circle which we can write. You might remember from high school or something. It's the equation x squared plus y squared equals 1. So that's a circle of radius 1 centered at the origin. So what have we done? It's pretty simple, but we've gone from a Pythagorean triple to a rational point on the unit circle. Just like in the other derivation of Euclid's formula that you saw, the hard direction is the opposite direction. Can we take a rational point on the unit circle and get a Pythagorean triple? That's the question. It turns out you can, and I'll show you how to do that. So here's how we do it. Let me draw a circle. The unit circle, in fact. There's a circle. Let's draw the coordinate axes. Try and go through the center. I make no claims about my artistic ability, so it's just going to have to be close enough. Okay, and just for completeness, let's label that's the x-axis, this is the y-axis. Okay, so the question is, which rational points do we have on the unit circle? I mean, do we even have any? Well, yes, we actually have four easy ones, which are I'll just mark them, but I'll erase the marks in a sec. We've got so-called North Pole, South Pole, and also the right and leftmost points. Those are all rational points on the unit circle, but we're going to just focus on one of them. Just this one that makes the algebra work out a little bit more neatly. Let's call this point P. Its coordinates are -1 and 0. So that's a perfectly valid rational point on the unit circle. Now the trick, well, not really a trick yet, but first let's suppose we have another rational point. Doesn't really matter where it is, just not the green point again. Take any other point, rational point on the unit circle. So let's call it point Q, coordinates x0, y0, with both of those coordinates in the rationals. And we know there's at least one other such choice. There's the North Pole up there that we could have picked, although we're going to assume, we're not going to say anything about its coordinates. It's going to be a general such point on the unit circle. I would say the main trick to the derivation that we're going to do is to connect those 2 points, those 2 rational points on the circle, with a straight line. Okay, what does that do for us? Well, now this slope gives us a new quantity. T, we'll call it. It's the slope of this line. And elementary formula, T is equal to change in y, which is y0 minus 0 over x0 minus 1 over change in x. So that's the slope of that line. And now our goal is to use this information to find some expression for x0 and y0. And we hope that that'll lead us to deriving the expressions up here for a, b, and c that I wrote. Okay, so let's do it. What do we know? We have 2 equations that those points x0 and y0 satisfy. We know that x0 squared plus y0 squared equals 1. Let's call that equation 1, and that's because those coordinates are on the unit circle. We assumed point Q is a point on the circle. We can also rearrange that equation for the slope to get a somewhat nicer expression. Y naught equals t times x naught plus 1. It's equation 2. Now this is a system of equations, which you might have seen a little bit of in linear algebra, but they're not linear equations. So there's not always a standard way to solve these sort of systems, but this one turns out to be sufficiently nice that we can work with it. So how do we start? Well, we substitute equation 2 into equation 1. So we've got a nice expression for y naught. We can replace y naught in equation 1 with that. So we get x naught squared plus t squared, x naught plus 1 squared equals 1. Expand that bracket a little bit, we get x naught squared plus t squared times x naught squared plus 2x naught plus 1 equals 1. And now I'm going to skip a couple steps just to save time, but what we want to do is collect terms by the degree of x naught. So all the x naught squared terms we collect, and we get t squared plus 1 times x naught squared. All the x naught terms, we get 2t squared times x naught. And the remaining terms, we get t squared minus 1 equals 0. In other words, we have a quadratic in the variable x naught squared. And we know -1 is a root. Why do we know -1 is a root? Well, we know by construction that the green point up there, -1 comma 0, lies on both the circle and the line that we drew. So we know it has to be a root, and you can check by direct substitution that x naught equals -1 satisfies that equation. So we want to find the other one, and you can do this with the quadratic formula that I'm sure you're all familiar with, but a more interesting way to do it is with something called Vieta's formulas, or Vieta's relations for the roots of a polynomial. So if x naught is the other root, then the product of the two roots of that quadratic, I should have mentioned, we know it has two roots because it's a quadratic, and so -1 is one root. By construction, x naught is the other root, which is distinct. And so the product of the two roots has to be, by Vieta's formulas, it's equal to, in this case, the constant term divided by the leading coefficient. So t squared minus 1 over t squared plus 1. So of course we rearrange that and we get x naught equals 1 minus t squared over 1 plus t squared. Just rewrote the bottom so it looks a little bit more symmetric, I guess. Okay, so we have an expression for x naught in terms of t. Can we do the same for y naught? If we can, then we have a pretty good understanding of how to find x naught and y naught, how to characterize them. And in fact, we can use equation 2. We could use 1 or 2, but equation 2 is much simpler. It'll give us an easier way to find y naught. So let's use equation 2. So, equation 2 says y naught equals t times x naught plus 1. Now we know an expression for x naught. It's 1 minus t squared over 1 plus t squared. plus 1. Well, instead of plus 1, I should do plus 1 plus t squared. Over 1 plus t squared. What do we get? Well, you can see when we add those fractions, the order 2 terms, the degree 2 terms cancel, so we just get a 2. And multiply it by the t on the outside of the brackets, and we get that. Y naught equals 2t over 1 plus t squared. It's very windy today in Waterloo, so hopefully you can't hear the wind whistling outside. Hopefully it's not too loud. Okay, great. So we've got expressions for x naught and y naught in terms of t. Now let's remind ourselves what t was. Let me just copy this picture here. Oh, I guess I should have copied the y. Well, whatever. Let's paste that down here. There. Okay, so t was the slope of this blue line connecting the green and blue point on the circle there. But what do we know about t? Well, we know that t, let's put it in red because this is an important part of the proof, t is rational. Why is that? Well, look how it's defined. It's y naught over x naught plus 1. Y naught is rational. We assume that. We assume that x naught and y naught was a rational point on the unit circle. And x naught is in Q, so therefore you add a 1 to a fraction, it's still a fraction. X naught plus 1 is a rational number as well, of course. Okay, well that's promising. So if t is rational, why don't we write t as a fraction? Is fraction n over m, and this is suggestive notation. Might be able to predict where this is going, but again, we don't need to assume anything about primitive Pythagorean triples. We'll just say that m and n are integers with, of course, m not equal to 0, otherwise it's not a valid rational number. So t is rational, we can write it as a fraction. Okay, what can we conclude? Well, remember we had expressions for x naught and y naught right up here in blue boxes. So we said that we found that x naught was equal to 1 minus t squared over 1 plus t squared. With that notation for t, that definition for m and n, we get that x naught is 1 minus n squared over m squared over 1 plus n squared over m squared. Multiply the top and bottom by m squared and you get m squared minus n squared over m squared plus n squared. Some quantities that you might recognize from the very beginning of the lecture, or from yesterday's lecture, the last lecture. Similarly, we had an expression for y naught. It was 2t. T is now n over m over the same denominator, 1 plus n squared over m squared. So, yeah, we multiply by m squared on top and bottom again, and we get y naught is 2mn over m squared plus n squared. Okay. So you might be able to see the punchline already, but let's just to be explicit, let's write it out. So we wanted to get a Pythagorean triple out of the point x0, comma y0, rational point on the unit circle. So how do we do that? Well, let's let a equal the numerator of x0, it's m squared minus n squared. B is the numerator of y0, 2mn. C is the denominator, m squared plus n squared. So clearly a, b, and c are all integers because m and n were both integers, we said. We defined t as n over m up there. So the question is this a Pythagorean triple? Well, of course it is, because we know that x0 squared plus y0 squared equals 1. That's from equation 1. In other words, that's just saying that the point x0, comma y0 is on the circle. It's equation 1 up here that we started with. So equation 1 gives us, just matching up what everything is equal to, a over c squared plus b over c squared equals 1, which is equivalent to a squared plus b squared equals c squared. So yes, A, B, C is a Pythagorean triple. So we were able to derive the exact same formulas, Euclid's formula, using a very different method. So yes, we can go the other way. We can take a rational point on the unit circle, the point Q in blue there, and we produce a Pythagorean triple. So we can go both ways. And so Pythagorean triples can be thought of as nothing more than rational points on this circle. Okay, now you might be asking yourself, what's the point of proving the same theorem in two different ways? Well, one thing is just because it's interesting, right? It's a PMATH course, so you should, at some point you have to accept that some questions are just inherently interesting. Of course, one proof is enough. The proof that you did in Tamash's video earlier this week is enough to prove the theorem, to prove Euclid's formula, but it's interesting and insightful to have a second proof. As mathematicians, is something that we're inherently interested in. But it also gives us perspective, and it makes us ask, okay, well, we looked at the intersections of lines and circles here. Maybe there's something more interesting here. There's something bigger going on. It turns out there is, and it's called algebraic geometry. Just talk a little bit about algebraic geometry. Actually, technically, what we just did was arithmetic geometry, because we were looking at rational points on a geometric object, but algebraic geometry is the more general discipline. So AG, algebraic geometry, can be described as the study of systems of polynomial equations. And I mentioned this very briefly when we wrote down that system of two equations above. So it's a study of systems of polynomial equations. So we had two quadratic equations. Well, actually no, one quadratic and one linear. And we studied that system of two simultaneous equations. And algebraic geometry is the general study of that. This generalizes linear algebra. Why is that? Well, linear algebra is the study of polynomial equations where each polynomial is, the name implies, is linear, degree 1, or I guess degree 0 in the degenerate case. So this generalizes linear algebra. As we saw above, you can have higher degree polynomials in that still something we want to study. And I'll just say that algebraic geometry is much harder than linear algebra because, well, linear algebra, you probably have taken a course or two on that so far. It's pretty much all figured out, right? We have a system of finitely many linear equations and finitely many variables. We can say precisely when it has solutions, how many solutions it has, etc. It's more or less figured out. And that's not true at all for algebraic geometry. There's so many seemingly easy problems in algebraic geometry that we haven't figured out yet. So in linear algebra, you kind of learn about this problem from a geometric perspective, where you look at intersections of lines and planes, hyperplanes, and higher dimensions. In algebraic geometry, this corresponds to intersections, again, of geometric objects, but they're more complicated. So it's intersections of general curves, or what you call algebraic curves, because they're described by algebraic equations or polynomials. So it's the intersection theory of curves, surfaces, etc., higher dimensional shapes. And so that's exactly what we did above. We looked at the intersections of a straight line and a circle. Those are intersections of two curves. So speaking of curves, I'm going to just tell you about, in the last part of this lecture, I'll tell you about a very important class of curves called elliptic curves. You might have heard of them before in a number theory class, in like 135, I'm not sure. Maybe if you talked about cryptography, they might have come up. But they're very important geometric and number theoretic objects, elliptic curves. So, again, modulo my artistic ability, let's draw a picture to see what's going on. So an elliptic curve is an equation of the form y squared equals x cubed plus ax plus b. So it's quadratic in y and cubic in x, and you can transform the equation so that a lot of the terms drop out. Well, technically this is what you call the affine version of the equation. You actually need to do something called a projective completion to make it valid in algebraic geometry, but don't worry if that means nothing to you. But let me try and draw an example. So this is probably going to be rough to watch, but bear with me. So again, I'm drawing the axes here. Are those perpendicular? No, not at all. This one's not horizontal. That's probably... Oh no, I could do a little bit better. Okay, good enough. This is the coordinate axes, x and y. I'm going to draw a specific elliptic curve. They can look pretty different. It's fun to look at pictures of them on Wikipedia or something, but the one I'm going to draw looks something like this. That's supposed to be symmetric about the origin, but it's not a circle. It's a weird oval, pinched oval sort of shape. Okay, and it has this other part that looks kind of like a sideways mountain or something. Okay, so let's call this the curve E, and it's defined by the equation y squared equals x cubed minus 2x plus 1. And the exact equation doesn't matter too much, I just thought it looked interesting. But one reason that elliptic curves are so important is we have a way to define an addition operation, a group operation on the points of the elliptic curve. So let's take point P, some point over here on the curve, another point Q. Then let's connect them. Let's connect them with a straight line. Okay, that looks about right. Close enough. And so that straight line that goes through those 2 points hits the curve, the elliptic curve, in a third point, call it R. Then we reflect that point about the x-axis, so we flip it horizontally down here. Looks like it's around there. That's what we call the negative of R, the point that we flipped. But we define that to be equal to the sum P plus Q. So we define the sum of the points P and Q this way. We connect them with a straight line. They intersect the elliptic curve in a third point, reflect that point horizontally, and that's the sum of the 2 points that we started with. Seems like a weird definition, but, well, you can tell it's the right definition if you study this a lot, because you see that this operation gives you a group structure, an abelian group structure, in fact. This gives the curve E. Well, it works for any elliptic curve. We're just drawing a specific example. This gives the curve E an abelian group structure. I'm assuming you've at least come across that definition before. Perhaps you learned about vector spaces, it came up, but just to remind you, that means that this operation has an identity element. Actually, the identity is it's what's called the point at infinity. It's kind of a wacky thing to think about, but it is there. So we have an identity element. It's associative. Each point has an inverse. Suggestive notation, the inverse of point P would be minus P. We just reflect it horizontally, so around there. Every point has an inverse, and it's commutative. That's why it's an abelian group. So most of those things aren't terribly hard to show, but the associativity of this group operation is actually quite tricky to show. If you take an introductory course in algebraic geometry, they'll probably talk about that, or some equivalent formulation of the group of an elliptic curve. So that's remarkable. Most curves and surfaces and whatnot don't have a group structure like this. And if they do, they're called abelian curves or abelian surfaces, etc. Elliptic curves are a very important class of abelian curves. So in other words, the points on an elliptic curve form an abelian group. Okay, so if E was our elliptic curve from before, then we see the rational points I should say the set of rational points on E, the elliptic curve, is denoted by E of Q. And an extremely long research program in sort of modern math has been to study E of Q for general elliptic curve E. It's very difficult, but very interesting, because as you've seen above, it lets us answer a lot of questions about number theory with geometry. So E of Q, turns out, is a subgroup of E with its elliptic group, with its abelian group structure. So that means if you, for one, it means the identity element, which I call this point at infinity, has rational coordinates. We consider it an element of EQ, and EQ is closed under addition and in negation, reflection about the x-axis. So a huge amount of work has gone into studying E of Q. Whoops. Every time someone proves a theorem, a significant theorem about E of Q, it's a huge event in this subject in math. People win Fields medals for these sorts of things. So one example, which was and still is a very celebrated theorem, is called the Mordell-Weil theorem. Louis Mordell is a British mathematician, I believe, and André Weil is French. So Mordell proved a version of it, and then Weil came along later and generalized it. Mordell-Weil theorem says that E of Q is finitely generated. So it's a finitely generated abelian group, which means we know a lot about what it should look like abstractly. If you've taken a course on group theory, introductory course on abstract algebra or something, then you know that such a group looks like a bunch of copies of the integers with some other finite groups added on. So that means, basically it means E of Q as a group is isomorphic to a bunch of copies of the integers. In fact, well, it's finitely generated, so some finite number of copies times some finite groups. Those are called the torsion parts. This is called the free part, just the z's at the beginning. And so a natural question is, how many of these do we need? And so that's called the rank. Rank is the number of copies of z that you need to do the direct product of to get the whole group E of Q. And so once you find out that E of Q is finitely generated, you know it has a finite rank, and so one natural question to ask is, well, what's the rank? And how do we compute a rank of a given elliptic curve? Is there an upper bound so that every elliptic curve has a rank lower than or equal to that given rank, that specified upper bound? And there's really not much we can say about it, and so that's a subject of a very important problem in math called the Birch and Swinnerton-Dyer Conjecture. It's kind of a mouthful, but this is, in fact, you might have heard of it, this is one of the Millennium Problems. It's a problem posed by the Clay Mathematical Institute. So supposedly it's on the same level as the Riemann hypothesis, P versus NP, and things like that. Basically, it's one of the most important unsolved problems in mathematics at the moment. And I won't get into it because it's very technical, but I'll just say that it concerns the rank of E of Q. It relates the rank to these other objects called L functions, and certainly if you can solve it, you'll be extremely famous. So I think I'll stop here. So just to recap, what have we done? We've proved Euclid's formula for Pythagorean triples using a totally different method. We showed that Pythagorean triples are in one-to-one correspondence with rational points on the unit circle. We did that by analyzing the intersection of the circle with a straight line. That led us to a discussion about algebraic geometry, which is concerned with generally systems of polynomial equations. And in particular, elliptic curves are a very important class of curves that you can study. One reason they're important is because their points have an abelian group structure, which is kind of convoluted definition, but it's nevertheless works. In particular, the points on an elliptic curve with rational coefficients also form a group under this operation. They're a subgroup. And so an enormous amount of work has gone into studying E of Q. We know it's finitely generated, but for example, we don't know much about the rank. So if you can say something new about the rank, then you'll be pretty famous. Okay, that's it. I'll talk to you guys soon.